Hi, my name is Donald Nguyen. I'm presenting work on a lightweight infrastructure for graph analytics. This is joint work with Andrew Lenharth and Keshav Bengali at the University of Texas at Austin. So briefly, what is graph analytics? These are algorithms to compute properties over graphs. They're very difficult to implement on large scale because the data sets are large, and in order to have high performance, you need to support parallelism and have efficient runtime systems. Contributions of our work are a lightweight infrastructure for graph analytics based on improvements to the Galois system, which is an existing system for exploiting parallelism. One improvement that I'm going to describe here in this talk is our implementation of priority scheduling. Through these improvements, we're able to achieve orders of magnitude performance improvement over third-party graph analytics DSLs for many applications and inputs. The reason we observe these improvements is mostly due to the fact that Galois supports a more general programming model, which allows better algorithms to be written. Secondarily, Galois has a better infrastructure for shared memory parallelism, which improves our performance. The outline of my talk is in three parts. First, I'm going to describe an abstraction for graph analytics applications and its implementation in the Galois system. Second, I'm going to describe one improvement to the Galois system that we did for graph analytics, namely priority scheduling. Third, I'm going to evaluate applications written in the Galois system compared to applications written in various graph analytics DSLs, and we're going to look at their performance. So, one example of a graph analytics application is the single source shortest paths problem. We are given a graph and would like to find the shortest distance between a source node and all other nodes in the graph. There's many algorithms for solving this problem, and they mostly revolve around labeling nodes with tentative distances, and then iteratively improving those distance estimates until we converge on a final correct answer. As an example, look at the edge up on the upper right. Here we have an edge where the source of the edge, its distance label is 1, and the destination of the edge, its distance label is 9. The edge connecting these two nodes has a weight of 3, so we can improve our distance estimate from 9 to 4. This operation in SSSP is called an edge relaxation. Sites in the graph where we can perform an edge relaxation, I'm going to call an active edge and color them in red. It turns out different algorithms for solving SSSP are just different schedules of applying the same core edge relaxation operation. As an example, one algorithm for solving SSSP is chaotic relaxation. In this case, we just arbitrarily pick active edges, process them. Processing active edges may create more active edges. We continue processing them until there are no more active edges left in the graph. Another algorithm for doing SSSP is Bellman-Ford. Here, we apply the edge relaxation operator over all the edges in the graph, g times. Another algorithm for doing SSSP is Dijkstra's algorithm. Here, we use a priority queue to order our active edges by the source of the active edge, and we process them in ascending distance order. One parallel implementation of SSSP is delta stepping. It uses a sequence of bags to prioritize work. Each bag stores active edges with approximately the same distance label. What we see here is that different algorithms are just simply different schedules applying the same operator, namely the edge relaxation operator. And for SSSP in particular, we need priority scheduling for the most work-efficient algorithms. Some terminology. I've already introduced the concept of an operator, like edge relaxation. It's applied at a certain site, an active edge or an active node. One instance of applying an operator at an active edge is an activity, and the area of the graph that's read or written by executing an activity, I'm going to call the neighborhood of that activity or operator. So Nicholas Wirth has a very famous motto, which is program equals algorithm plus data structure. In our experience, parallel programs are operators plus schedules plus parallel data structures. One way to understand that is to ask, what is the operator? In two graph analytics DSLs that I'll talk about later in the presentation, like Ligra and Powergraph, what an operator is a vertex program. What is a vertex program? It's a program or operator where the active element is a node, and your neighborhood can only be your direct neighbors in the graph. In contrast, the Galois system provides the capability to have unrestricted operators, so your neighborhood could potentially be the entire graph, and you're allowed to morph the graph potentially by adding nodes and edges or removing nodes and edges. Another question one can ask is where or when does an activity or operator execute, or where is it scheduled, or how is it scheduled? One common choice is autonomous scheduling. Here, activities execute transactionally. So consider the case on the bottom. We have two activities, AC and BC. If we're executing using autonomous scheduling, either the AC activity will execute followed by the BC activity, or vice versa. Another option is to use coordinated scheduling. Here, activities execute in rounds. So we may be in a situation where both the AC activity and the BC activity execute at the same time. We'll produce multiple updates to the C node, and based on some problem-specific reduction technique, those multiple updates will be reduced to a single value. The Galois system is simply a direct implementation of this motto of parallel program equals operator plus schedule plus parallel data structure. Users write their operators with respect to the Galois data structure library, and then they provide a high-level description of how they want their operator to be scheduled. The Galois system, in turn, provides concrete implementations of schedulers and of the data structures that the user uses. In turn, these schedulers and data structures are built on top of a library that supports thread primitives like barriers, mutexes, etc., and a parallel memory allocator. This, in turn, runs on a particular machine. The results I'm presenting here are results on a multi-core machine, but we actually have results using GPUs, large-scale NUMA machines, and distributed memory systems. So that briefly summarizes our abstraction for graph analytics, namely, parallel programs equal an operator plus a schedule plus a parallel data structure. Now I'm going to describe one improvement that we did to the Galois system to support graph analytics. Just some background, in Galois, the way scheduling is done is that there's a library of different scheduling policies. Think of LIFO, FIFO priority scheduling, and users use a domain-specific language to specify how, and at a high level, how operators should be scheduled. That high-level description is given to the Galois system, which is responsible for synthesizing a concrete implementation, namely a scheduler. So I mentioned before in my description of SSSP, the best algorithms for computing and solving this problem require priorities. So what is one way of implementing priorities? We can use a concurrent priority queue. These are widely available, but in our experience, they don't scale very well because of the overheads of using a current priority queue, given that our tasks are very small, very fine-grained. Another option to do is to use a sequence of bags, where each bag stores work at a particular priority level. This is what's used in the delta stepping algorithm, for instance. It turns out there's a high overhead for finding non-empty urgent priority bags when one uses this data structure. Our solution to this problem is a scheduler called ordered by metric, or OBIM. It's a sparse sequence of bags with one bag per priority level. But in order to reduce synchronization, the sequence itself is replicated among cores, and the bag itself is distributed between cores. In order to reduce the overhead for finding work, we're going to use a reduction tree over the machine topology to get an estimate of the current best urgent priority to work on. In the interest of time, I'm only going to describe how the sequence and the bag data structures are implemented. If you would like to know more about the reduction tree, please see the paper. So the scheduling bag. So the scheduling bag is responsible for storing work at a particular priority level. You can think of it as an unordered collection of tasks. But in reality, it's concretely implemented as a distributed data structure. We have cores, each of which has at most one block, which is filled with tasks. And each package or socket in the machine has a linked list. If we'd like to enqueue work at a core 1, and we have a non-full block, we can simply add that work to the corresponding block. When that block becomes full, we enqueue it on our per package linked list, and then we create a new block to store subsequent work items. If we'd like to retrieve work and we have a non-empty block, we simply retrieve it from the non-empty block. In the case that we don't have a block, we can fetch a new block from our per package queue, like so, and retrieve work. And only in the very rare case when the currently executing core doesn't have a block, nor does the package corresponding to that core have any work in its per package queue, do we fetch work across packages. In this way, we minimize communication in a modern multi-core machine. If you recall the first session of SSSP, someone was talking about ways to improve synchronization. This is one way to reduce the cost of synchronization. So that describes the scheduling bag, which stores work at a particular priority level. The next part of the OBIM scheduler is a priority map, which maps priority levels to the scheduling bags I described in the previous slide. It's implemented in order to improve performance is that there's a global map, but that global map is replicated locally to each core. But these replicas are allowed to contain only a subset of the entries that are contained in the global map. In particular, our local map for core 1 has mappings for priority level 0 and priority level 1, but not priority level 3. And our mapping, and our local map for core 2 has mappings for priority 1 and priority 3, but not for priority 0. Let's say, through our reduction tree technique, the cores have agreed that priority 1 is the priority that they would like to do work on. If core 1 needs new work, it simply fetches work from that corresponding bag. If, for instance, core 1 would like to add work at a particular priority, in this case priority 3, it looks in its local map, notices there's no such mapping for a priority 3, looks at the global map, notices there is a mapping for priority 3, so it simply copies that mapping to its local map and then queues into the corresponding scheduling bag. If core 2 wants to enqueue work at priority 5, it performs the same sort of sequence of steps. It looks at its local map, notices there's no such mapping for priority 5, looks at the global map, and notices in this case there's no mapping for priority 5 at the global map as well. So only in this very rare case does core 2 lock the global map, insert a new mapping for this priority 5, and enqueue into the corresponding scheduling bag. So that summarizes my description of how priority scheduling is implemented in the Galois system. And now I'm going to describe our evaluation of applications written in the Galois system versus those written in graph analytics DSLs. So as you might have heard from this talk and previous talks, there's many systems for doing graph analytics. Many DSLs have been proposed recently in the literature. And it turns out it's easy to implement many of these APIs for these DSLs on top of the Galois system. The reason being the Galois system provides more general support, so many of these graph analytics DSLs are just special cases of programs that the Galois system already supports. In particular, I was able to re-implement GraphLab on a shared memory machine on top of Galois. Likewise, I was able to implement another DSL for graph analytics, Ligra, on top of Galois. These implementations are called GraphLab G and Ligra G in this talk. It only took a few hundred lines of code to do each. Our evaluation is straightforward. We have a single multi-core machine with 40 cores, and I'm going to show results for 5 different applications. One is breadth-first search. Second is connected components, which was mentioned in the previous talk. Third is computing the approximate diameter of a graph. The fourth is to do one iteration of the PageRank algorithm. And the fifth is the single source shortest path problem that I introduced earlier. I'm going to show results for 2 inputs. One is a Twitter graph. This is slightly different than the Twitter graph that was mentioned before. It's a little bit bigger in the previous talk, sorry. One thing to know about the Twitter graph is it's scale-free, and it has a very low diameter, which means its longest shortest path is very short. In particular, its diameter is approximately 10 or 20 steps. In contrast, our other input is the road network of the United States. The graph is much smaller, but has much higher diameter. In particular, its longest shortest path is around 8,000, 9,000 steps. In my comparison, I'm going to compare with Ligra, which is a shared memory DSL for graph analytics, as well as PowerGraph, which is a distributed memory DSL for graph analytics. For comparison, I'm only going to run PowerGraph on a single machine. It supports threaded parallelism, so it's not an unfair comparison. And I'd like to note, as an aside, we actually ran PowerGraph on a distributed memory system using 64 machines, each of which having 16 cores. And the performance that we achieved on PowerGraph in this configuration never beats the performance we were able to achieve using Galois on a single machine, assuming that input fit the memory. So on to the results. Here on the top panel, I'm showing results for the Twitter graph. On the bottom, the road network. Along the x-axis are 5 different applications: BFS, connected components, approximate diameter, PageRank, and SSSP. Here, the y-axis are Ligra running times divided by Galois running times. So values greater than 1 indicate how many times the Galois application for solving that particular problem was faster than the Ligra application for solving the same problem. On the Twitter graph, we can see speedups up to 10. On the road network, we can see speedups up to 300. Now, some portion of this performance impact is due to the fact that Galois supports a much more general programming model. So in order to in that general programming model, one can implement very efficient algorithms. Ligra supports a much more restricted programming model, so in order to solve the same problems, it often has to resort to more restricted and less efficient applications. The other factor in performance is the Galois system has a pretty optimized implementation of many low-level threaded primitives, and those primitives equally could be used to improve the Ligra system as well. In order to measure the impact of this second factor, let's compare performance of Ligra versus Ligra G. Recall, LIGRA-G is just our implementation of the LIGRA DSL on top of the Galois system. Here, you can see that in general, it's better to run LIGRA programs in Galois than rather than using the existing LIGRA system. But the magnitude of our performance impact is not large enough to cover the space that's shown in the left side of the figure, which says the majority of the impact that we see from running Galois comes from the ability to support more expressive programs rather than the better implementations of low-level shared memory primitives. We did a similar comparison with Powergraph. Here, again, the top figure shows the Twitter graph. The bottom shows results on the road network. Again, x-axis is BFS, connected components, computing the approximate diameter of the graph, PageRank, and single source shortest paths. Again, these are runtime ratios. Here, we can see performance improvements up to 1,000x on the Twitter graph and up to 10,000x on the road network. Again, we did a comparison with Powergraph versus Powergraph-G, and again, we can see that in many cases, it's much better to run Powergraph programs on top of Galois rather than running the Powergraph system itself. In some cases, we can achieve speedups up to 50x. So a little bit more detail into performance results. I told you that some part of the performance is due to the better implementations, but again, most of the impact is due to the better algorithms that are supported in the Galois system that aren't supported in particular graph analytics DSLs. As an example, as I told you before, the best algorithm for doing SSSP requires ideas of priorities. That's directly implementable in the Galois system, but that is not supported in Powergraph. That has a very direct impact on performance. Likewise, for connected components, the best algorithm we've found to solve the connected components problem uses a union-find or disjoint set data structure. That data structure is not a vertex program. Therefore, again, we see this issue where supporting a more general programming model allows you to write a better program. And as a general note, the Galois system uses autonomous scheduling in general, which is required for supporting high diameter graphs, whereas Powergraph uses coordinated scheduling, which on high diameter graphs requires many rounds of computation, and that induces a lot of overhead for these types of inputs. This only briefly summarizes the content of my paper. In particular, in the paper, there's results for more inputs, more applications. There's also a more detailed discussion of our performance results. We also talk about other infrastructure changes that were needed for the Galois system, in particular, how to support non-priority scheduling and how to support scalable parallel memory management. Also, we have results for out-of-core DSLs. So, in summary, the Galois system is a general programming model which permits efficient algorithms to be directly implemented. The Galois infrastructure is lightweight. In particular, we're able to layer several other graph analytics DSLs on top of the Galois system, in many cases outperforming the original implementations. All these results are available online at the website cited below. Thank you for your attention, and I'm ready to take questions.
Terrence? Hey, doesn't work?
It does now. Hello, Terrence Kelly, HP Labs. I was wondering, in your comparisons, your performance comparisons, did you compare against simple serial code of the sort that an undergraduate might write for any of these algorithms? Because some of them have very simple textbook implementations.
So in the paper, we don't include such conclusions, the comparisons, but I will tell you that in most cases, the Galois version of these applications is at least within 2x of what a sequential implementation of these graph algorithms are. And for some inputs, like the Twitter graph, there's additional optimizations that are not present in undergraduate versions of these applications, which are very important and give you additional performance improvements.
So I'm just interested in the magnitude of the performance improvements. So for instance, I have a copy of the Twitter 40 graph.
Yeah, so as an example.
Last night I implemented connected components. It's not many lines of code, and it ran in under 20 seconds. On an aging laptop, 1 core. You're presenting comparable runtimes on a 40-core machine.
So let me talk about the BFS application. So in that case, recent people have found that for scale-fair graphs, it's important not to do sort of what's called in the paper just a push implementation. You need to alternate between push versus pull. And using that type of optimization for BFS, you can get about a 2x performance improvement. For connected components, it's right that a label propagating algorithm on the Twitter graph is reasonably okay. But for road networks and for other types of structures of graph, the disjoint union-find data structure tends to be better in parallel. And its performance is actually better than the label propagating algorithm on one thread.
So I have a related question. So basically the graph that you're using, the Twitter graph, it would take at most 10 gigs of memory. So how efficient is your platform in efficient memory usage? Because you are using 128 gigs of memory to actually process a graph that requires less than 10 gigs of memory.
So I think a more general point is that for graph analytics, there is an element of scale involved, but there's also an element of structure. So the road network is even smaller than the Twitter graph. It's less than a gigabyte. But when you give that input to these graph analytic systems, they ground to a halt. It's not about the size in this case, it's about the structure. So I will say that there's very important stuff to do about scaling out the system to larger inputs and more efficiently, but there's also a point that I think is unrecognized here, which is it's important to understand the structure of the graph and the structure of applications.
Yeah, I have a follow-up, but I'll get back to you later.
Okay, thank you.
Kui from Carnegie Mellon. Seems that your experiment is conducted on a single shared memory machine. And why don't you compare with the single machine version of hardware, which is essentially GraphG, and comparison with GraphG, and also can you run on distributed memory cluster of machines?
Well, thankfully, the first question is easy to answer. Those results are in the paper. The second question is we're currently working on a distributed memory implementation of Galois. One thing I will note as a data point is that we're able to scale this implementation without much change to a large-scale NUMA machine, up to 500 cores. In those cases, if you know, to scale up to even these types of data systems requires actually studying things about locality, data placement, et cetera. So we have pretty good confidence that a distributed memory version of this implementation is feasible. But like I said, that's future work.
Okay, thank you.
So cyberspace is eerily quiet. So I'll add a question. Are stragglers an issue at all in Galois? And if so, have you plans for dealing with them?
I presented sort of the bag schedule that I showed before. It's actually a way of implementing work stealing, which is one way to at least alleviate the problem of stragglers on a shared memory machine.
Okay, thank you very much.